Okay, so last section we'll look at this week is 3-5. So we'll start off with a quick review of complex numbers and just a couple reminders about some things we've already said, but still important. So remember that if a number is a 0, we have 5 different ways to say that. If a number is a 0, it means the number is a root. It means if you plug that number into a function, you'll get 0 as the answer. But it also means that that's an x-intercept. If you find a number that's a root, you just found the number on the x-axis where the graph crosses. So if you draw a polynomial like this one, x squared plus 1, let's see what it looks like. It's over here. So here's a picture of x squared plus 1. If you look at that graph, I'm just going to put it over here, I'll make it a little smaller. Where does that graph cross the x-axis? Well, not the y-axis. I agree, it does cross the y-axis at 1. But as far as this axis, it doesn't. So if it doesn't cross the x-axis, there are no real zeros. It doesn't mean there isn't a number you can't plug into this equation and get 0 as an answer. It's just that the number you have to plug in is imaginary. Okay, that's the key. Okay, so we'll come back to that in a little bit. But I just want you to see here, if a graph never crosses the x-axis, then that means it has no real answers. Okay? It could just have imaginary. Any questions why there's no real answers here? Okay. The other thing too is the calculator cannot find the imaginary answers. The only way we could do this is with algebra. All right, so just a couple reminders. This is kind of the review part, which we'll go through quick. We'll talk about what I is, and then we'll just go over very quick how to add, subtract, multiply, and divide. All right, so I is the square root of -1. Why? Because it's kind of like if you asked me, why don't parallel lines cross? Because they don't. That's the definition. That's the way it's defined. When you say parallel, in my head I think they don't cross, just the way it is. That's how this is. I equals the square root of -1. Basically, somebody made that up. That's what it is. But as long as we all agree on that, we all agree, okay, I equals the square root of -1 for whatever reason, as long as we're all on the same page, then we're okay. It's like we all believe the same thing. I squared. Well, if I is the square root of -1, that means you have this. I squared. Well, what happens when you square and square root? Becomes just the number, right? The square and the square root, they kind of cancel each other out, and all you're left with is -1. That's important because when we multiply complex numbers, you're going to get I squareds. You should never leave I squared in the final answer. I squared always should be changed into a -1. Okay. Any question on that? Okay. So let's look at the equation we just had and see what happens. Let's plug I into the parabola that I just drew for you. I squared plus 1. What did we just say I squared is? It's -1. And what's -1 plus 1? 0. That means that I is a root of this equation. You just found a root. You found something that you can plug in and get 0 as the answer. It's not real. It's imaginary. Any question on why when you plug in I, you get 0? Okay. Well, we'll get to this in a little bit, but equations like this never have just one imaginary root. Equations with imaginary roots always come in pairs. So if you have one imaginary, you automatically have another one, and it's very easy to figure out the other one. I'm going to show you that in a little bit. So, when we write a complex number, if it has a real part and an imaginary part, we usually do it in this order. Real part, plus, or it could be minus, and then the imaginary part. A is the real part, B is the imaginary part. So here's an example right there of a complex number that has a real and an imaginary part. Real part's 2, imaginary part's 3. Here's another one. The real part is 2/5. The imaginary part, I didn't write it, but what number is in front of I? Right, a 1, or in this case, a -1. So imaginary part is -1. If you want to write the 1 in, you can. Now, these other ones are still complex numbers, but they're a little different. 3i. Well, the imaginary part is 3. Bless you.
Thank you.
What's the real part?
1.
Well, if it was 1, I would have had to write it like this. 1 plus 3i, so you knew it was 1. If it's not there, it's 0, right? So the real part there is 0. The real part there is 0. Bless you. I don't know, maybe we shouldn't do imaginary numbers, right? Maybe people are allergic. That'd be a good idea. No, I think exposure is good. Little exposure for the allergy makes you resistant to it.
I don't know.
I'm not buying it. So 4... Yeah, it doesn't. I don't think it really works that way with all kinds of allergies. Especially food allergies. I think they get worse. So 4, there's no imaginary part. You can think of it this way. 4, it's really a complex number. It's just there's no imaginary part. If the imaginary part is 0, or the real part is 0, we usually don't bother writing it. Okay? So those are all examples of complex numbers. All right, so complex arithmetic. So we'll go over how to add, subtract, multiply, and divide. First, when you're combining like terms, like 2i plus 3i, the answer is 5i. It's just like 2x plus 3x is 5x. So you can treat I like a letter when you're combining like terms. And if you're thinking, well, what do you mean treat I like a letter? Isn't I already a letter? No. I is not a letter in math. Okay? If you think I is a letter, that's like saying this is a letter. That's not a letter in math. Okay? That is a Greek letter, but in math it stands for the number 3.14, and it keeps going. So we know that when we do math with that symbol, we're not writing Greek. We're not writing a letter in Greek here. We're representing the number 3.14. Same thing. I is a letter in the English alphabet, but in math, when we write that, everyone knows we mean that number, the square root of -1. Okay, so in math, I is a number, just like pi. Okay. When we use multiplication, we're going to end up doing FOIL, or some people call it double distributive property, and that's going to result in I squared popping up. Anytime we get an I squared, we've got to change it to -1. To do division, we're going to end up talking about what's called a conjugate. And remember how I told you that imaginary roots always occur in pairs? Well, it has to do with conjugates. Which is nice because that means once you know one root, if it's imaginary, you automatically know another one. So it's like you get 2 for 1. Right? Automatically get 2 answers at the same time. Okay, and square roots. Okay, square roots are going to come up when you do quadratic formula, and you might end up with something like this. Well, we don't want to leave it as the square root of -9. We can simplify. So that's what I'm going to show you right now. So if I had the square root of -x, what number is in front of x, even if it's not written? Yeah, in this case, it's a -1. So if you want, you could think of it that way. It's the square root of -1 times x. It's -x. Well, when you have a product, you can break it apart so that each factor has its own root. The square root of -1 times the square root of x. And that we know the answer to. What's the square root of -1? I. So basically what ends up happening is anytime you take the square root of a negative, the negative symbol comes out from under the root and it turns into an I because of what I showed you right there. Other than that, taking a square root is exactly the same. It's just if there's a negative under there, put an I on the outside and get rid of the negative under the root. Okay, let's look at an example. Let's try the square root of -7. Okay. Anyone think they could tell me what that would be following the pattern up above? Yeah.
7i.
Not quite. 7i would be the answer to this problem. The square root of -49. The answer would be 7i. But this, you can't really do much with the number under the root. Like 49 you can because it's a perfect square. 7's not. Yep, Sam?
Would it be I, the square root of 7?
Just I square root of 7. It's just like the problem up above, but x is a 7. So it's I square root of 7. Okay, let's do one that we can simplify. The square root of -4. What would that one be? Yep.
2.
That would be the answer to this problem. That has an answer of 2. This one doesn't. Yep. 2i. Now, without me even telling you, some people put the I after it, but then in the first one we put the I before it. That is how you do it. The only reason we put the I before the square root is because if you write this, that looks confusing to me. I'm not sure if you mean the I is under the root or is it not under the root. If you put the I in front, that eliminates that confusion. Okay? That's the only reason when you have a square root, we put the I in front. Other than that, we usually put the I after it, just like we would if it was a letter. Okay? How about this one? Square root of -9. What's that one? Yep, Shai?
It's 3i.
Yep, 3i. Okay, and let's try the square root of -20. Well, what do we know right away the answer is going to have in it? It's going to have an I in it. So now let's treat the rest of the problem like it was this. What two numbers can you multiply to get 20? And one of the numbers you're thinking of has to be a perfect square. Yep.
4, 5.
4 times 5. And the reason I said it has to be a perfect square is because now you can simplify. What's the square root of 4? 2. So if the problem was the square root of 20, it would be 2 square root of 5. The answer here is going to be 2i square root of 5. Okay, that's a square root. Mess that up with that. Okay, so square roots work exactly the same. Just make sure you put an I on the outside. Question on square roots. Okay, let's look at one example of add, subtract, multiply, and divide. Add and subtract are very easy. Those are very quick. Multiply and divide, not as quick. Not super hard, but not as fast. Okay, So we want to think of combining like terms. The first parenthesis has a real part of 7. The second parenthesis has a real part of 4. The operation they want me to do? Addition. So you can combine real with real, imaginary with imaginary. So if I combine the real part in the first one and the second one, what do I get? 11. If I combine the imaginary in the first plus the imaginary in the second, what do I get? Positive or negative 2i? Positive 2i. And that's it. So just combine the real, imaginary with imaginary. Now, subtraction works almost the same way, except remember what you do when something's on the outside of parentheses like that? Think of it as distributing that negative. So the real part is really negative 6, and the imaginary part is negative 1i. Okay. Both of those are being subtracted. So if I do that, what would my real part be? Yep. Yep. 4 minus 6 gives me negative 2. And how about my imaginary part? Yeah, Jay. Negative 2i, take away I, is negative 3. Okay, so that's adding and subtracting. Now, if you look at the next problem quickly, it might look kind of like the same thing. Parentheses, another set of parentheses. The big difference is there's no plus, there's no minus. If there's no plus or minus there, what operation are we doing? Multiplication. So that you can put the dot if you want to remember, but you need to put, you got to remember it's multiplication. All right. And for this is how you do it. Okay. So let's do it together. 2 times 5, 10. 2 times negative I, negative 2i. 5 times 3i, 15i. And now let's look at the next part in steps. Positive times negative. What's a positive times a negative? So it's a negative. Start with that. 3i times I. We already took care of the negative. 3i squared. All right, so I've got 10. I can combine those. What's negative 2i plus 15i? So that's 13i. And now this part at the end, we have minus 3 I squared, but I squared is what number? So we've got to remember to change that to a negative 1. Now we've got 10 plus 13i. Right, it's minus a minus. Right, we've got 2 minuses, that turns into plus 3. Think of it as negative 3 times negative 1. Now we've got 10 plus 3. That's why we changed I squared to negative 1. We can combine it with something else. What's 10 plus 3? 13. Just a coincidence that the real and the imaginary part came out the same. That usually doesn't happen. Bouncing around. Any questions on that one? Okay, so I think that's a good place to pause. When we come back, we'll look at division using conjugates. Okay, so last thing we're going to review before we look at finding some roots and stuff is division. But to do division, we have to know what a conjugate is. So, very simply, a conjugate is just the complex number, but you change the sign of the imaginary part. That's what negate means. Change the sign of. So if you had a plus bi, the conjugate is a minus bi. Just change the sign of the imaginary part. Don't do anything to the real part. Okay, let's just practice seeing if we can find some conjugates. So if you had 3 plus 2i, what would be the conjugate of that?
3 minus 2i.
That's the conjugate. What we're going to do with that, I'll show you next, but that's the conjugate. How about 4 minus 5i? 4 plus 5i. Okay. What about 3i? Negative 3i. If you want to think of it as like 0 plus 3i, the conjugate is 0 minus 3i. We don't normally put the 0. We just write it like that. How about 6?
It would just stay 6.
It would stay 6. If you're wondering, well, how does it stay 6? Think of this as 6 plus 0i. The conjugate is 6 minus 0i. Plus 0 minus 0 doesn't change. It's the same thing. Okay. So we would just write 6. Any questions on finding conjugates? All right. So where do we use conjugates? Division. So if you have a division problem, and they want you to divide 2 complex numbers, you're not allowed to leave I in the bottom. Ever. You can't leave I in the bottom. So how do you fix having I in the bottom? That's where the conjugate comes in here. So to divide 2 complex numbers, multiply the top and the bottom by the conjugate of what's in the bottom. So, to divide these, it says multiply the numerator and denominator, so I already set that up, by the conjugate of the denominator. What's the conjugate of the denominator here? Yeah, we'll go Jake.
2 plus 3i.
2 plus 3i. Let's start with the top. Nothing special is going to happen here. We just have to do it all out. So we get 5 times 2. We get 5 times 3i. So in my head, I'm just going to think, okay, 15i and 2i. 15 and 2 gives me 17. So that's 17i. And the last part is I times 3i. Okay. And if we want, we can do it all at once. Well, I times 3i is 3i squared. But I squared is what number? So that's really negative 1 times 3. Or minus 3. Now, watch what happens in the bottom. Okay. Looking at it quick, I already can tell you the bottom is 13. When you do the whole thing now. Right. I'm going to show you how I know that. What's 2 times 2?
4.
We get 4. Watch what happens with the next 2 parts. 2 times positive 3i, 2 times negative 3i. They cancel out. So the outer and the inner, you don't even need to pay attention to that part. They always cancel out when you have conjugates. And then the last part, this part I just kind of did in my head. Negative 3 times positive 3 is how much? Negative 9. But then I also have I times I, which is I squared. Anytime you have an I squared, it just changes the sign. So this is going to be what number when you do it out? Positive 9. So the way I got 13 in my head quickly is I just did that number squared and that number squared. 4 plus 9. If you don't want to use that shortcut, you don't have to. You can just FOIL it out every time. Just remember, you're always going to get stuff that cancels, so it's a waste of time to do it out. All right. Now let's finish it up. So we get 7 plus 17i over 13. Now, the only problem with that answer is when we write it in standard form, it should look like this. Real part, plus or minus, imaginary part, and then an I. So that's what it should look like. This is like a big fraction with the 13. So the way we can write it in standard form is put the 7 over the 13, and this is plus, and then put the 17 over the 13. So it's like you're just writing each one separate. So the real part is 7/13. The imaginary part is 17/13. As long as you understand that this and that are the same thing, that's important for the test. Multiple choice question, I would write the answer this way, not where the arrow is pointing. Okay, but it's not super hard to go from the last step to this step.
Since 17 over 13 is an improper fraction, would you ever simplify it?
No, I would always leave it like that. Now, if let's say it was 7 over 14, then yes, I would. If it was 7 over 14, I would write it as 1/2. But yeah, improper fraction, you don't simplify. If you can't reduce it, you can't reduce it. This one doesn't reduce. Any questions on that one? So dividing is really just multiplying by the conjugate. Great. So now let's look at the same kind of problems we've been doing all week. We're still going to be able to use synthetic division. Still going to use the rational root theorem. Except now the answers might have I. Okay, so the rest of this will be kind of like review. Except the answers might have I. Okay. What kind of equation is that? Because of the highest exponent is a 2. It's a quadratic. We already have a formula for solving quadratics. We can just plug it into the quadratic formula and we're done. No synthetic division, no rational root theorem, if the highest exponent is a 2. But it won't always be a 2. I was trying to find one, but I'll find one later. What's A in this case? And B? And C? It's exciting. So they're all 1. So if we plug it into the quadratic formula, we get negative b plus or minus the square root b squared minus 4 times a times c all over 2a. So there's not really a ton of stuff to simplify here. You get negative 1 plus or minus, well, 4 times 1 times 1 is just 4. What's 1 minus 4? Negative 3 over 2. And now we talked about that earlier. When we take that negative out, it comes out as what letter? An I. So your final answer is negative 1 plus or minus I root 3 over 2. Yep. You can leave it. This problem didn't say to write the answer in standard form. It just said find the zeros. If it said to write it in standard form, then the one extra step would be write negative 1 over 2 plus or minus. How would we write that one? That's just separating the real and imaginary part. The real part is right here. The imaginary part is right there. They didn't say to do it on this one, but I just showed you in case one in the homework says to do it. Notice what kind of numbers these are. Negative a half plus root 3 over 2. Negative a half, change the sign. Minus root 3 over 2. What's that called when you change the sign of the imaginary part? It's a conjugate. And I told you earlier that whenever you have a problem, imaginary roots always come in pairs. What does that mean? Conjugates. So if you did a problem and 3 plus I happened to be an answer, and so is 3 minus I. It's automatic. So you kind of get 2 for 1. Okay, they always occur in conjugate pairs. And that's what I'm writing right here. Yep.
So if you just put it in the way with the plus and minus in it, then you don't need to write like both of them, just that one part?
No, you can write it as plus or minus, and that's fine. Yep. So in example 4, I said, notice that the two answers are conjugates, and that always happens. As long as you have an imaginary part. Okay? If you don't have an imaginary part, like the number 3, well, you can't really get the conjugate of it because it's the same thing. 3 is 3, like we did 6. 6 was 6. All right, so as long as you have an imaginary part, those would both have to be answers to the problem. If the first one was. Okay, so all the theorems that we've used and learned all week, they all still work. Okay, the remainder theorem still works. Synthetic division still works. I'm going to show you synthetic division, okay, with a complex number. Okay, it's not super bad, but there's a little bit more arithmetic than regular synthetic division because it is a complex number. So, it says to show that this is a root. Now, what does that mean? If something's a root, and, bless you, I divide it in, what's my remainder going to be? 0. So that's what should happen here. Let's see. So put your root on the outside. And it's not too bad because it's only cubed. It's not like it's to the 5th or 6th power. If that was the case, this would be pretty bad. But cubed is as high as you would ever have to worry about. And the numbers are going to be pretty easy. 1, 0, 1, 10. At least those numbers are pretty easy. All right, so bring down the 1. That's your first step. And now the first step, it's not bad. We do 1 minus 2i times 1. That's like doing this. Just multiply the 1 out. Is that going to change anything when we distribute the 1? 1 minus 2i times 1 is still 1 minus 2i. And now what do we do with those two numbers? In long division, we subtract them. But we add them with synthetic. Well, we're adding 0, so it stays the same. Okay, so the only part of this that's going to be a pain is just the next 2 steps. We have to multiply this times that. So that means we have to FOIL it out. So I'm going to do it off to the side. What's 1 times 1? 1. 1 times negative 2i. Another 1 times negative 2i. And then negative 2i times negative 2i. So that's a positive 4i squared, which is really negative 1 times 4, or negative 4. So let's see what we ended up with. 1 and a negative 4 gives me a negative 3. Negative 2i and negative 2i is how much? Negative 4i. And then we add it with what's up above. Well, there's never anything to add with the I. So that stays the same. But 1 plus negative 3 is negative 2. So we just have to do it one more time, and then we're done. Okay, and I'm hoping we get negative 10. That's what we should get. So let's see what happens. What's 1 times negative 2? Let's erase that. So we get negative 2. 1 times 4i. Negative 4i. So we're hoping for a plus 4i somewhere. What's negative 2 times negative 2i? Well, negative 2 times negative 2i, just plus 4i. That's good. Negative 2i times negative 4i. Well, what's a negative times a negative? Positive 8i squared. But what number is 8i squared? Negative 8. And what's negative 2 minus 8? There's your negative 10. So we get a remainder of 0. So other than the middle 2 parts, those were kind of a pain. The last part, negative 10 plus 10, that's pretty straightforward. So we got a remainder of 0, which proves that is a root. Questions on? The answer is just showing this work. That's how you write the answer. It's kind of like a proof, but you're just showing a calculation. That's the answer. Okay. Odd degree polynomials, like to the third power, fifth power. If you remember when you graph any odd degree polynomial, let's just do x to the third minus 2x. Okay, it doesn't matter. As long as the highest exponent is an odd number. Look at how that looks. It goes up forever. It goes down forever. Well, if a graph goes up forever and it goes down forever, and it's connected the whole time, you never lift up your pencil, are you going to cross the x-axis somewhere? You have to. So that's why odd degree polynomials will always have at least one real answer. So, odd polynomials go up and down forever and are connected, or we could say continuous. If you go up forever and you go down forever, and you never lift up your pencil doing it, you're going to go through the x-axis somewhere. That's why odd degree polynomials will always cross the x-axis at least once. This one crosses 3 times. Okay. But I could make it so it only crosses once if I did something like that. Should probably do it. Maybe. Yeah. So now it only crosses once. But it has to cross at least once. Okay. So that's almost like the graph I just drew. Not quite. But it says find all the zeros of x cubed minus 1. Okay. So the way you start the problem is exactly the way you did in the homework. Start with your p and q. Find rational roots. The problem with this is it's a cubic. We can't jump right to quadratic formula like we did here. Okay, can't use quadratic formula till we use synthetic division on this at least one time. So let's write our factors of p. What are the factors of 1? And the factors of q? Well, it's also the same thing, factors of 1 again. So what are all the different p over q's? It's just plus or minus 1. So we're going to graph this. But I don't even have to graph it. I can just tell. If you plug in 1, what's 1 cubed? Minus 1? There's your root. Okay, I can just tell by, it's short enough, I don't even have to graph it. If you plug in 1 for x, you get 0 for the function, which means 1 is a root. Okay? So we know 1 is a root. If you didn't recognize that, graph it. And look at your graph, and you'll see it crosses the x-axis at 1.
Instead of graphing, can we always just plug it in?
You can, yeah. It just gets a little annoying if it's a big problem, like 3x cubed minus 8x squared plus 9x minus 12. Then it takes longer. So, all right. So we know 1 is a root. 1x cubed, 0x squared, 0x minus 1. Bring down the 1. 1 times 1, 1. 0 plus 1, 1. 1 times 1, same thing again. And then 1 times 1, 1. Negative 1 plus 1, 0. Okay, we already knew we were going to get 0 because 1 is a root. That is my quotient. Now I need to solve this problem. 1x squared plus 1x plus 1 equals 0. So if I'm making a list of my roots, 1 is a root. And how would we solve this? Quadratic formula. Wait a minute. 1, 1, 1. 1, 1, 1. We already solved it. So at this point, you would now do what we did right here. Solve that equation, use the quadratic formula, and you get the answers -1/2 plus or minus root 3 over 2i. Those are the other two answers. Negative a half, plus or minus 3 over 2i. So see example 4. So we got 3 answers. 1 real, 2 imaginary. Could you ever get 2 real and 1 imaginary? You're always going to get 3 answers. No, you could never get 2 real and 1 imaginary, because what did I say about imaginaries? They come in pairs. So if you're gonna, you could either have 2 imaginary and 1 real, or you could just have all 3 real and no imaginary. Those are the only options that could happen. Yeah.
So you could never have like all imaginary?
No, you couldn't have all imaginary in this problem because it's an odd number of answers. If it was an even amount of answers, yes, you could. So, in the problems we were just doing, this is actually what I was just saying. The total number of answers equals the highest exponent. Highest exponent, where was the problem? Right here. Highest exponent was, where'd the problem go? Wasn't it x cubed minus 1 right here?
Yeah.
I don't know what happened there. I must have erased it. But highest exponent was a 3. 3 answers. Highest exponent was a 2. 2 answers. That always happens. So the total number of answers equals the highest exponent. And remember, since roots and factors are the same thing, right? If 2 is a root, x minus 2 is a factor. If 8 is a root, x minus 8 is a factor. Well, that means you always have the same number of roots as you do factors. So if you were going to factor a cubic, it would have 3 sets of parentheses. Right? So whatever you're factoring, look at the degree. As long as it's greater than 0. This doesn't apply if it's a degree 0. But if it's quadratic, cubic, anything higher than 0, you will have that many factors. What about, let's see, what if I had a problem where the highest exponent was a 5? How many factors would you get there? You would get 5. Now, they don't have to be unique. They can be repeated. Remember, we saw a graph yesterday where it did something like this. Touched the axis, it bounced away from it, and it went back up. When you have repeated roots, that's what happens. So there's still 5 answers here. The 5 answers are -1, -1, 2, 2, and 2. Those are the 5 answers. It's just some of them are repeated. So we can say that -1, the fancy way to say repeated is how many times you see it. It's called multiplicity. So -1 appears twice.
What would make it a triple root like that?
A triple root, what would it look like if you drew it? I can just type it in real quick and show you. So you got x plus 1, x plus 1. I'm pretty sure with the double root, it's going to come up, it's going to touch it and bounce away. I think the triple root's just going to go right through. Just going to look like it goes right through it. X minus 2, x minus 2, and x minus 2. So I'm thinking at -1, it'll bounce away from it, and at 2, it'll just go right through. Now, it goes right through, but it actually did a little curve in there. Yeah. But it did bounce away from it like I thought there. Not exactly what I thought. Right there. But that's what it would look like.
So that kind of makes sense because it would be acting as a x to the 3rd power essentially for that part, in the way x to the 3rd power is when it reaches 0.
Kind of looks, yeah. Yep. So 2 is a root of multiplicity 3. Repeats 3 times. Alright, so a little quicker than I would have liked to go through it. We would have had about 20 more minutes normally. Could have slowed down a little, but pictures took a little bit. So. Any questions on that? Okay, so that's homework for tonight. Those are just the odds. So it's 1 through 3 odd, 9 through 13 odd, 15, 19 to 22, and then 25, 27, 32, 36, 39, and 40. Okay, so I will be here after school if anyone needs extra help. We have our second to last test for the term tomorrow. And I think that's it.